There is a question that haunts every thinking civilization. Not when we will die or how our sun will expire, but something far more absolute. How will everything end? Not just our world, not just our galaxy, but the entire cosmos, every atom, every law of physics, every possibility of existence itself. This is not a question born from curiosity. It is a question born from terror. The terror of knowing that we live inside something finite, something dying, something that began and must, by the very logic that governs reality, conclude. For thousands of years, humanity looked up and saw eternity. The stars seemed fixed, unchanging, immortal. We projected our hopes onto that darkness, imagining heavens that would outlast us, realms beyond decay. But then we learned to do mathematics. We learned to measure distances that break the mind, to calculate forces that dwarf our comprehension, to peer into the machinery of creation itself. And what we discovered was not comforting. We discovered that the universe is not a monument, it is a process. And every process has an ending. The first person to truly confront this was not a philosopher, but a physicist. In the 19th century, as steam engines roared and industrialization transformed the world, scientists were obsessed with a new concept: entropy. Heat always flows from hot to cold. Order always decays into disorder. Energy spreads out, becomes useless, dissipates into equilibrium. And if this was true for engines and ice cubes, why wouldn't it be true for everything? Why wouldn't it be true for the stars themselves? The realization struck like a hammer. The universe is running down. Someday, every star will burn out. Every temperature will equalize. Everything will become the same cold, dead, motionless expanse. They called it heat death. We call it the Big Freeze. And for over a century, it seemed inevitable. But there was another possibility, a stranger, more violent ending. What if the universe didn't fade away? What if it came roaring back? Before we can understand how the universe will end, we must understand what it actually is. This seems simple. Look up, there's the universe. But what you see with your naked eye is a lie. The stars you observe, the galaxies captured by our most powerful telescopes, the light that has traveled billions of years to reach your retina, all of this represents less than 5% of what exists. 5%. Imagine trying to understand a book when 95% of the words are invisible. That is cosmology. We know the universe is approximately 13.8 billion years old. We know it contains at least 2 trillion galaxies, each harboring hundreds of billions of stars. We know it is expanding, that every galaxy is racing away from every other galaxy, carried by the stretching of space itself. But we also know that the matter we understand, atoms, molecules, the stuff of planets and people, is a rounding error in the cosmic census. 27% of the universe is dark matter, a substance that exerts gravity but emits no light, passes through ordinary matter like a ghost, and defies every attempt at direct detection. We know it exists because galaxies rotate too fast to hold together without it, because light bends around invisible masses, because the structure of the cosmos would collapse without its gravitational scaffolding. But we cannot see it, cannot touch it, cannot even define what it is made of. And then there is the truly disturbing component, dark energy. 70% of everything that exists is this substance, this force, this property of space itself that pushes the universe apart. It does not clump like matter. It does not dilute as space expands. It simply is, everywhere, at all times, an anti-gravitational pressure that grows stronger as the universe grows larger. We discovered it by accident. We were trying to measure how much the expansion of the universe was slowing down, how gravity was gradually winning its ancient war against the outward momentum of the Big Bang. Instead, we found that the universe is accelerating, gravity is losing, and dark energy is why. This discovery did not just change cosmology, it murdered the most elegant ending the universe could have had. 1998 was supposed to be a triumphant year. Two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were racing to measure the deceleration of the universe using supernovae as cosmic distance markers. Type 1a supernovae are remarkably consistent in their brightness, which makes them perfect standard candles. If you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it is. By measuring supernovae at various distances, the teams could map the expansion history of the universe, see how fast it was growing at different epochs, and determine its ultimate fate. The expectation was simple. They would measure how much the expansion had slowed down over billions of years, calculate the density of matter, and determine whether the universe would expand forever or eventually collapse. It was a measurement problem, not a philosophical one. The answer was out there in the data, waiting to be extracted. But when the data came in, it made no sense. The supernovae were dimmer than expected, much dimmer, which meant they were farther away than they should be, which meant the universe had expanded more than the models predicted, which meant something was pushing it apart. At first, they assumed it was an error. You do not overturn a century of cosmological assumptions because of anomalous data. You check your instruments, your calculations, your assumptions. Both teams checked everything. The result did not change. The universe was not slowing down, it was speeding up. And the only way to explain that was to resurrect an idea Einstein himself had called his greatest blunder: the cosmological constant, a repulsive force embedded in the fabric of space itself. The discovery earned a Nobel Prize. It also condemned the universe to a specific fate. The Big Crunch, the idea that the universe might one day stop expanding and collapse back into a singular point, was now all but impossible. Gravity had been fighting a losing battle for billions of years. The expansion was accelerating. The future was not a fiery implosion. It was an endless, lightless cold. But let us imagine for a moment the world that might have been. Let us imagine the universe that gravity could have built if only there had been enough matter to feed it. The Big Crunch is beautiful in its symmetry. The universe begins in infinite heat, infinite density, infinite curvature. It explodes outward, expands, cools, forms structure, stars ignite, galaxies swirl, life impossibly emerges, but all the while gravity is pulling backward. Every atom exerts a tug on every other atom. Slowly, imperceptibly, the expansion loses momentum. Galaxies that were once receding begin to slow, then stop, then fall. At first, the reversal would be subtle. Astronomers in that distant era would notice that the most remote galaxies were blue shifting instead of red shifting, that light was being compressed instead of stretched. The cosmic microwave background, the faint afterglow of the Big Bang, would grow hotter. The night sky would brighten. And then, over millions and billions of years, the universe would begin to shrink. Galaxies would collide more frequently as space contracted. Stars would merge in cataclysmic explosions. The temperature of the cosmos, which had been falling for eons, would begin to rise. At first, it would be comfortable, like the warmth of a spring morning, but it would not stop rising. The universe would continue to compress, to heat, to intensify. Eventually, stars themselves would be torn apart by the density of space. Atoms would ionize, then disintegrate. The universe would become a plasma, a soup of subatomic particles indistinguishable from the conditions of the early Big Bang.
And then, as the compression accelerated, even the structures of physics would break down. Space and time would curve toward infinite density. The laws that govern cause and effect would cease to function. Everything that had ever existed, every thought, every civilization, every photon that had traveled across the void, would converge into a single point of infinite heat and infinite curvature. The Big Crunch, a cosmic implosion, the end of all endings. It would be terrifying, but it would also be meaningful. The universe would complete a cycle, returning to the conditions from which it emerged. Some physicists even speculated that the crunch could trigger another Big Bang, that the universe might oscillate eternally, dying and reborn in an endless rhythm. It was a vision of cosmic reincarnation, a universe that never truly ended but only transformed. But this is not our universe. The reason the Big Crunch failed is brutally simple. There is not enough matter. The fate of the universe is determined by a single parameter, the density parameter omega. If omega is greater than 1, the universe is closed, finite in size, and destined to collapse. If omega is less than 1, the universe is open, infinite, and will expand forever. If omega equals exactly 1, the universe is flat, balanced on a knife edge between eternal expansion and eventual collapse. Measurements of omega have been refined over decades using the cosmic microwave background, the distribution of galaxies, and the observed acceleration of expansion. Every measurement points to the same conclusion. Omega is almost exactly 1. The universe is flat. But critically, when you account for dark energy, the total energy density is dominated not by matter, but by this repulsive force. The universe is flat, but it is accelerating. The expansion will never stop. The collapse will never come. The mathematics behind this are encoded in the Friedmann equations, derived from Einstein's general relativity. These equations describe how the scale factor of the universe, how much space has stretched since the Big Bang, changes over time as a function of energy density and pressure. When you plug in the observed values for matter, radiation, and dark energy, the equations produce a clear prediction. The universe will expand forever, at an ever-increasing rate. Galaxies beyond our local group will accelerate away from us until they cross the cosmic event horizon, the boundary beyond which their light can never reach us. The universe will become lonely, and then it will become dark. The Big Freeze does not happen all at once. It unfolds over timescales so vast that the entire history of human civilization, from the first stone tools to the present day, is less than a single heartbeat in comparison. We are living in what cosmologists call the stelliferous era, the age of stars. It is a golden age, a brief window of cosmic time when the universe is filled with light and heat and complexity, but it will not last. Star formation depends on the availability of hydrogen gas, the raw material from which stars are born. Over billions of years, this hydrogen is gradually consumed. Some is fused into heavier elements inside stellar cores. Some is locked away in dead remnants, white dwarfs, neutron stars, black holes. Some is ejected into intergalactic space by supernova explosions and galactic winds. With each passing generation of stars, less fuel remains. Galaxies become redder as massive blue stars die and are not replaced. Star formation slows, then sputters, then ceases entirely. The last stars will be small, dim red dwarfs, sipping their hydrogen fuel so slowly that they can burn for trillions of years. But even they will eventually exhaust their reserves. Around 100 trillion years from now, the last red dwarf in the universe will flicker and die. The stelliferous era will end, and the degenerate era will begin. In this era, the universe will be populated not by shining stars, but by their corpses. White dwarfs, the dense cores of sun-like stars, will float through the darkness, gradually cooling from white-hot to dull red to black. Brown dwarfs, failed stars that never ignited fusion, will drift like dead embers. Neutron stars, the collapsed cores of massive stars, will spin in silence, their radio pulses long since faded. And black holes, the densest objects in the universe, will lurk in the void, occasionally devouring stray matter that wanders too close.
But even in this darkness, processes will continue. White dwarfs will occasionally collide, triggering brief, violent explosions. Brown dwarfs will capture rogue planets, heating them momentarily through gravitational friction. And slowly, over timescales of 10 to the 40th years, protons themselves may decay. Proton decay is predicted by some grand unified theories, but it has never been observed. If it occurs, it means that even atomic nuclei are not permanent. A proton, left alone for long enough, will spontaneously disintegrate into lighter particles, positrons, neutrinos, gamma rays. If this happens, then every white dwarf, every dead planet, every remnant of the stelliferous era will gradually evaporate into radiation. The very atoms that once formed planets and people will cease to exist. The universe will become a thin gas of particles and photons spread across incomprehensible distances, drifting toward equilibrium. But the black holes will remain for a long time. Around 10 to the 40th years, when the last atoms have decayed or been swallowed, the universe will enter the black hole era. These objects, once thought to be eternal prisons from which nothing could escape, are themselves mortal. In 1974, Stephen Hawking discovered that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly faint, inversely proportional to the black hole's mass. A stellar mass black hole emits so little radiation that it would take 10 to the 67 years to evaporate. A supermassive black hole, millions or billions of times the mass of the Sun, could take 10 to the 100 years. These numbers are not just large, they are incomprehensible. The current age of the universe, 13.8 billion years, is 10 to the 10th years. A trillion years is 10 to the 12th. We are talking about timescales a Google times longer than the universe has currently existed. But quantum mechanics is patient. The black holes will evaporate, particle by particle, slowly converting their mass into energy. And when the last black hole finally dissolves in a brief flash of gamma rays, the black hole era will end. What remains is the dark era, an ocean of photons stretched by cosmic expansion into wavelengths larger than galaxies. Occasional electrons and positrons separated by distances greater than the observable universe is today. The temperature of space will approach, but never quite reach, absolute zero. The expansion will continue, accelerating, pulling every remaining particle farther and farther apart. There will be no structure, no energy gradients, no possibility of complex systems. Entropy will reach its maximum. The universe will achieve heat death. This is the Big Freeze, not a sudden catastrophe, but an asymptotic approach to nothingness. The universe will not end with a bang or a whimper. It will simply fade, becoming ever colder, ever emptier, ever silenter, forever. But cosmology is not a closed book. There are possibilities we have not yet discussed, scenarios that are stranger, more violent, or more hopeful than the standard model predicts. The Big Rip is one such scenario. If dark energy is not a cosmological constant, but a more exotic form of energy called phantom energy, its density could increase over time. As space expands, this energy would grow stronger, accelerating the expansion at an ever-increasing rate. Eventually, the expansion would become so violent that it would overcome the forces holding matter together. First, galaxy clusters would be torn apart, then galaxies, then solar systems, then planets, then molecules, atoms, and eventually even atomic nuclei. Space itself would be ripped to shreds in a final cataclysm, perhaps 20 billion years from now. Then there are cyclic models, inspired by theories like loop quantum gravity and string theory. These propose that the Big Bang was not the absolute beginning, but a transition from a previous cosmic phase. The universe might undergo eternal cycles of expansion and contraction, each big crunch seeding a new Big Bang. Or we might exist in a multiverse, where our universe is one bubble in an infinite foam of universes, each with different physical laws.
And there's the false vacuum scenario. Quantum field theory suggests that what we perceive as empty space might not be in its lowest energy state. We could be living in a false vacuum, a metastable state that could spontaneously decay into a true vacuum. If this happens, a bubble of true vacuum would nucleate somewhere in the universe and expand at the speed of light, obliterating everything in its path, rewriting the laws of physics as it spreads. We would have no warning. One moment, existence. The next, annihilation. These are not idle speculations. They are possibilities permitted by our current understanding of physics. The fact that we do not know which is correct is a testament to how much remains unknown. How do you test predictions about events trillions of years in the future? How do you verify theories about the ultimate fate of existence when every experiment must be completed in a human lifetime? This is the observation problem, the epistemological nightmare at the heart of cosmological eschatology. We can look backward. Light from distant galaxies shows us the universe as it was billions of years ago. The cosmic microwave background is a snapshot of the universe when it was only 380,000 years old. By studying these ancient photons, we can reconstruct the history of the cosmos and extrapolate forward. But extrapolation is not observation. We are making predictions based on the assumption that the laws of physics do not change, that dark energy remains constant, that no unknown forces will emerge in the deep future. These are reasonable assumptions, but they are still assumptions. There is a deeper problem. We are trying to understand the ultimate nature of reality using brains that evolved to hunt, gather, and avoid predators on the African savanna. Our intuitions are calibrated for medium-sized objects moving at moderate speeds. The cosmos operates on scales where intuition fails. Infinity, entropy, quantum vacuum decay, these are concepts we can truly grasp, only approximate through mathematics and metaphor. And yet, we persist, because the alternative, ignorance, is intolerable. To know that everything ends is a burden unique to conscious beings. Animals do not mourn the heat death of the universe. They do not lie awake wondering whether protons decay. Only we do. Only we have the cognitive machinery to understand our own insignificance, to map out the full trajectory of cosmic history, and to realize that everything we build, everything we love, everything we are, is temporary. This knowledge could be crushing, and for some it is, but it can also be clarifying. If the universe is finite, if time itself has an endpoint, then every moment becomes precious. You are not just a collection of atoms. You are a collection of atoms that can contemplate the end of all collections of atoms. You are the universe experiencing itself, knowing itself, mourning itself. That is not nothing. There is a concept in physics called the Boltzmann brain, a thought experiment about entropy and probability. In a universe approaching heat death, quantum fluctuations could spontaneously assemble a functional brain, complete with false memories, for a brief instant before it dissolves back into chaos. If you wait long enough, truly long enough, far beyond the timescales we have discussed, such fluctuations become not just possible, but inevitable. The universe could produce infinitely many Boltzmann brains, fleeting sparks of consciousness in an otherwise dead cosmos. Some physicists take this as evidence that our current cosmological models are flawed. Others see it as a strange kind of hope. Even in the dark era, thought might emerge, however briefly. But we do not need to wait for quantum miracles. We are here now. We exist during the stelliferous era, the age of light, the brief window when the universe is comprehensible and beautiful. That is an extraordinary privilege. Still, humanity has never been content to accept fate passively. We are the species that looked at the sky and built machines to reach it. We are the species that split the atom, decoded our own DNA, sent messages to the stars. If the universe is dying, perhaps we can save it or escape it. Some physicists have speculated about manipulating dark energy, finding a way to reverse or neutralize its effects. If dark energy is a property of space itself, and if we could alter that property, we might be able to halt the acceleration, even trigger a contraction. This would require technology so advanced it borders on magic, engineering at the scale of the cosmos itself. But physics does not forbid it.
Others have proposed fleeing into artificially created universes, baby universes nucleated from our own through controlled manipulation of quantum fields. If we could create a new space-time and transfer information into it, consciousness might survive the death of this cosmos by migrating to another. We would become the gods of our own creation, abandoning a dying universe for a fresh one. And then there are the truly audacious ideas, becoming beings of pure information, existing as patterns in quantum fields that could persist even as matter decays, slowing our subjective experience of time so that 1 trillion years feels like a single moment, or finding loopholes in thermodynamics itself, ways to extract energy from the vacuum or harvest the evaporation of black holes. These are fantasies, for now, but every technology that defines modern life, flight, nuclear energy, computers, medicine, was once a fantasy. The difference between impossible and inevitable is often just a matter of time. One day, billions of years from now, the last star will die. It will be a red dwarf, small and dim, and its death will not be dramatic. It will simply cool, fading from red to brown to black over millions of years. Perhaps there will be observers then, descendants of humanity or some other conscious lineage, beings so altered by time and technology that we would not recognize them. They will watch as the last light goes out. What will they think in that moment? Will they mourn? Will they feel what we feel when we contemplate our own mortality, the ache of knowing that something precious is ending? Or will they be beyond such emotions, their minds restructured to accept the inevitable with calm detachment? Maybe they will remember us, the species that first asked the question, the species that looked at a universe full of light and dared to imagine its ending. We are the ones who measured the distances to the stars, who calculated the expansion rate, who discovered dark energy. We are the ones who mapped the trajectory of doom. But we are also the ones who existed at the perfect time. Not too early, when the universe was a hostile fireball. Not too late, when the stars have gone dark. We live in the age of light, the golden age, the brief epoch when the cosmos is alive with energy and complexity and possibility. We are the lucky ones. And perhaps that is enough. Perhaps the meaning of existence is not to last forever, but to witness, to understand, to appreciate the improbable beauty of a universe that could have been nothing more, but instead chose to be something for a little while. The universe will end, but it has not ended yet. And until it does, we are here, thinking, questioning, searching for answers to questions that may have none. That is not defeat, that is defiance, and it is glorious.